We are Senior Lab Group 13, and we will be discussing our analysis from the biodiesel experiment. The group members are Mohammed Al-Fashki, Connor Evans, John Reynolds, Ethan St. John, and Lucas Wider. The purpose and the reason of this experiment are as follows. Investigate the production and purification of biodiesel at bench scale and pilot scale. Then use modeling to help aid in understanding of the experiment. Understanding the role of gas chromatography, centrifugation, and sample washing has to the industrial and undergrad setting. Identify potential sources of error. Make recommendations about how the lab can be changed for future labs. Investigate the scale up and scale down of the production of biodiesel.
The bench scale experiment was performed in a 1-liter glass reactor outfitted with an impeller, temperature probe, and removable heating jacket. A stopcock is attached at the bottom of the reactor in order to extract samples over the course of the experiment. The setup for the pilot scale has both a reactor and washing vessel. The washing vessel was not used for the experiment, however. Due to the increased material required at the pilot scale, the reagents had to be pumped into the reactor instead of simply being poured in like at the bench scale. The samples collected needed to be washed and centrifuged in order to extract all the aqueous components from the samples and leave only the organic components. There are some important safety considerations for this experiment. Both methanol and potassium hydroxide can be dangerous if handled improperly. Methanol is toxic and can cause blindness if ingested. The boiling point of methanol is 60 degrees Celsius, so it was mixed with the preheated oil to ensure that there were minimal concerns with methanol vapors escaping into the laboratory. The flash point of methanol is 12 degrees Celsius, which is below the ambient temperature of the lab, so there are also flammability concerns with using this reagent. Potassium hydroxide is caustic, meaning it can cause chemical burns if it comes into contact with the skin or other organic tissue. If inhaled, chemical burns can occur in the mouth, nose, throat, and lungs. When handling the potassium hydroxide pellets, a face shield, in addition to the standard personal protective equipment, was worn to mitigate this risk. If spilled, soybean oil can cause a slipping hazard and must be cleaned up immediately. Additionally, working with hot oil can cause burns and must be handled with care.
A mathematical model was provided in MATLAB to study the batch production of FAME to determine feasible operating conditions and also to study the kinetics of the reaction. The kinetics of the system were modeled using mass action kinetics and not the elementary reactions because the concentration of the catalyst would be too hard to determine in real time. To determine the effect that the different rate constants had on the production of FAME, and sensitivity analyses were performed for the reaction system at both 10% and 50% increase and decrease. As you can see from the plots, rate constants 1 through 3 had a significant effect on the production of FAME for both increasing and decreasing by 10%. However, when the increase and decrease level was increased to 50% overall, the effect on FAME production was mitigated in the positive direction. Rate constants 4 and 5 had the opposite effect of the other ones, i.e. reactions 4 and 5 would decrease the production of FAME, meaning they were undesirable for the final design of the reaction system. As previously mentioned, the MATLAB code also allowed us to look at initial conditions and also operating conditions to optimize and corroborate the results found in the bench scale and pilot scale reactions. The input parameters used by the model included the initial mass of triglyceride, the weight percentage of potassium hydroxide, the methanol to soybean oil molar ratio, the reactor temperature, and the reaction time. The model, however, did not take into account the mass transfer limitations or the scaling of the process, resulting in no observable effect by varying the initial triglyceride mass or the weight percentage of KOH. Therefore, only the molar ratio of methanol to soybean oil, the reaction temperature, and reaction time would give meaningful results. We altered the code to allow vector inputs for these three parameters. The two plots shown show the extremes of the molar ratio of methanol to soybean oil. As you can see in the leftmost plot, the lower ratio gives a much lower total yield of FAME, while as the higher ratio gives almost twice as much FAME yield. This indicates that this is the more optimal ratio to have for the actual testing, where our ratio will be 7:1 molar ratio. This is true even if the temperature is at the maximum we tested of 90 centigrade. However, when the molar ratio increased to 8.25, the spread of the data became much larger, giving that the lowest temperature that the reactor should have is 50 degrees centigrade and should run for at least 60 minutes.
The first of the two reactions to be run was the bench scale reaction. Bench scale reactions can be useful to understand the reaction without using too much material, while also providing a physical product to be analyzed. It's also easy to sample the reaction mixture throughout the experiment in order to get transient behavior of the reaction. Our reaction mixture was specified to have a 7:1 mole ratio of methanol to oil and 0.4 weight percent potassium hydroxide. 2.7 grams of potassium hydroxide were dissolved in 137.7 grams of methanol, and this solution was added to 600 milliliters of soybean oil, which was preheated to 60 degrees centigrade. The reaction was run for half an hour, and samples were taken every 5 minutes, and then one at the end after the reaction mixture settled. These samples had to be purified. The samples were mixed with water and centrifuged in order to separate out the organic layer containing the glycerides and the bottom layer containing all the unwanted components. The top organic layer was then taken using a syringe and washed with water again. This cycle was repeated 5 times, and then the samples were taken to the GC for analysis. Analysis by chromatography operates on the principle that the amount of sample passing through the detector at the time is proportional to the signal that the instrument creates on the software. Using this, the peaks that are created on the signal can be integrated in order to quantify the amount of sample that passed through the detector and therefore determine the composition of the sample that was injected. Shown here is an overlay of the 8 chromatograms obtained for our samples, 5 from the bench scale and 3 from the pilot. Specifically, the part that is relevant to our data analysis is shown here. You can see the monoglyceride peaks around 15 minutes, the diglyceride peaks around 18 minutes, and the triglyceride peaks around 22 minutes, and tricapper and the standard around 20 minutes. The glycerol peak was unable to be quantified effectively, so the 3 glyceride peaks had to be used for data analysis. In order to effectively analyze these, calibration curves of standards corresponding to each glyceride had to be created from reference data. These 3 standards are monoline, dialine, and trialine, and the calibration curves are shown here. It's the slope and intercept of these 3 curves that were used with equations given by ASTM in order to calculate the percent bound glycerin throughout the reaction in order to gain insight into the kinetics of how the reaction occurred. The percent of bound glycerin throughout the reaction can be seen on this plot. It follows an exponential decay, which is as to be expected. However, it does increase at 30 minutes. This could be a sign of reverse reactions occurring, or it's possible that there was an error in the collection, preparation, or analysis steps. The second day of the experiment included the pilot scale reaction. This was carried out using the same ratio of oil, methanol, and potassium hydroxide as with the bench scale, but instead of 600 milliliters, we used 200 pounds of soybean oil as a base. This was run for 45 minutes, and samples were taken at the very end from the bottom, middle, and top of the effluent. And then these samples were used and washed along with the bench scale reaction samples, and these samples were then analyzed along with them.
So we got a 99.08% average of FAME, as you can see in the mass percentage table, which has an agreement with the virtual lab results. For the percent bound glycerin, which are intrinsic for both bench and pile scales, because the pile had an average of 0.162% and the bench scale has a value of 0.177%, which are almost the same, and this can be used for scale up purposes.
Repeatability is defined as the difference between successive results, but only when the same operator, apparatus, and conditions are used. Advanced statistical methods are used to produce empirically driven equations, which of themselves are not statistical. In fact, the American Society for Testing in Materials, or ASTM for short, explains that repeatability is a non-statistical approach for analyzing experimental results. Although various expressions can be found in literature, ASTM has suggested the equations in the bottom left-hand corner for this biodiesel experiment. By contrast, reproducibility is the difference between two independent results made by different operators on the same apparatus. Once again, ASTM has suggested empirical equations derived from statistical methods not within the scope of this project. It should be noted that these expressions for repeatability and reproducibility are extremely useful when experiments are time-consuming or expensive. Approaches such as z-scores, t-tests, and ANOVA testing require many data points, whereas these methods only need as few as 2 data points for comparison. Unfortunately, since we only have our data, any comparisons are impossible, although future labs might consider sharing results to utilize these findings. Theoretically, properties such as temperature, pressure, mixing conditions, and controls are intrinsic, meaning they should remain the same regardless of scale. During scale-up, this is only partially true. Temperature can be maintained by increasing the surface area of a heating jacket, as demonstrated in the bench and pilot scales, and mixing can be altered by changing motor power or agitation paddle size. Materials are one of many things that don't always scale. Glass, for example, might be the material of choice for lab scale experiments, but having an industrial batch reactor made of glass is completely unreasonable. These are obviously made of materials such as carbon steel or cast iron. Additionally, economics are not intrinsic to chemical processes. When buying reactors, most economic correlations suggest power loss to be more appropriate for scale-up, which violates most assumptions of intrinsic behavior. Even the materials themselves depend on scale. Sigma Aldrich, for example, will sell customers a 100 milliliter bottle of high-grade methanol for nearly $45, while Alibaba has offerings starting at $1 per kilogram. Buying in bulk does have some disadvantages, such as the requirement to purchase at least 1,000 kilograms of product. While scale-up considerations are typically economically driven, scale-down processes often intend to generate predictive models through computational and analytical studies. Existing large-scale processes can be extremely expensive and time-consuming, especially in the case of the pilot-scale biodiesel experiment. Scaling down these processes to bench or lab scale greatly reduces material, energy, and labor costs, which makes repeated experiments more viable. By creating a design of experiments at the lab scale, dynamic modeling can be performed, which gives way to virtual processes. Nonlinear dynamic modeling was used in the virtual lab of this experiment, for example, which required almost no costs aside from human labor. By exercising the use of virtual processes, different conditions for large-scale processes can be modeled. The physical realizability of large-scale processes can then be predicted at a fraction of the cost of physical experimentation. Since the location of the experiment was in an outdoor shed, wind conditions and weather patterns affected results, usually through altering pressure gradients within the building or by fluctuating mass scale readings. A potential solution would be to relocate to a very well-ventilated room inside of the building. In fact, this provides an interesting project for future undergraduates involving the mass flow of fumes from the biodiesel compared to various ventilation rates. Additionally, reaction completion during the pilot scale was difficult to determine. Simply looking at the color of the product through the sight glass was unreliable, but might be more reasonable if a reference color was provided for undergraduates. Since centrifugation was by and far the most time-consuming aspect of these labs, experiments could be conducted to relate purity and centrifuge frequency. If, for example, similar results could be obtained from only 3 centrifuges rather than 5, then significant time could be saved.